Hi, I'm Aisha Siddiq. I'm a PhD student working with Dr. Hassan Warhawk at the University of Missouri. Today, I'll be presenting our work on security-aware approximate spiky neural networks. I will basically start from the motivation towards neuromorphic intelligence that is based on the spiky neural networks and what are their energy issues there and what are the state of the art works for approximate spiky neural networks, because approximate computing is a solution for the energy efficient consumption in SNNs. Then I will talk about the vulnerability of approximate SNNs to adversarial attacks, and then I will discuss our defense for adversarial attacks in AccSNNs and the results that we have. I will discuss that, and in the end I will conclude with some interesting takeaways. So there is a global trend in the neuromorphic shifts, and there's market size is increasing. Uh, and we are actually trying to develop neuromorphic chips with millions and billions of neurons embedded in them. Now, because these chips are driven by spiking neural networks, so that is possible to have such integration at low power. However, the size of SNNs is evolving. So we have even like spiking resonate with 100 layers. So there could be even more larger SNNs in the future. So now simulating larger SNNs would require more parameters in the training and inference phases that will eventually increase the energy consumption. So the challenge is like how to reduce the energy consumption of these accelerators where we have like Interlohi, Spinnaker or True North, etc. And one of the solutions is to have approximate computing then. In approximate computing, we minimize the computational effort for an acceptable energy goal. So it reflects the output quality of the error-resilient applications for the power or energy consumption. So let's say if we have a long ripple carry chain of adders, so if we break the carry chain, so now there won't be the longest critical path. So eventually the energy consumption will be low in this case. So we have basically approximated the design. And if we apply an image processing, where we have low image filtering, and if we replace the accurate adders with the approximate adders, then we can have energy efficiency. Like we, for example, like here in the second last image, like in this case, like we have less power, but there is no visual differences even though we have approximated the adder. But after this, there is a change in the visual quality, so we should stick with the second image. Actually, SNNs lack multipliers. Instead, they have adders that we can approximate. But approximate additions and with SNN simulations, that is non-realistic on the current GPUs because they do not have enough computational power. So we can have approximate computing by skipping the neuron connections. This even leads to 1.2 to 4x in improvement in the hardware efficiency when compared to accurate SNNs. The working principle is pretty same as an accurate SNN, that is like leaky integrate and fire neuron. We say that when membrane potential of a presynaptic neuron is higher than the threshold voltage VTH, then it generates the output spike that travels to the postsynaptic neuron to trigger their action potential, and this goes on. In an adversarial attack, an adversary can tamper the input images to the inference engine and add small perturbations to them such that they remain imperceptible to human eye but leads to misclassification or the catastrophic issues such as a serious car crash, because an autonomous car or self-driving car, for example, may interpret a stop sign as a 60 or 120 speed limit. In SNNs, we can have two different types of adversarial attacks in the state-of-the-art works. First is gradient-based attack, the other is neuromorphic attack. Gradient-based attacks are only for the wave-based images. They are just like the gradient-based attacks where we have basic iterative method or forced gradient descent method. In the neuromorphic attacks, they are basically targeted for the neuromorphic images. They modify the events there, and the examples are sparse and frame attacks. The neuromorphic images are basically acquired from dynamic vision sensor camera. The events are recorded only when a brightness variation in the scene is detected, and in the absence of the light changes, no information is recorded in the DVS camera image. So we can have adversarial defense against these attacks in the state-of-the-art works by crafting the noise and training the SNN with that, or we can have a training with another set of structural parameters, threshold voltage or time step, or we can have specialized noise filters such as background activity filter, etc. But all these works are targeted for the accurate SNNs. And when we talk about approximate SNNs, so their adversarial robustness is not explored so far. So consequently, there is a research gap in exploring the adversarial defense in AccSNN. Let's have a motivation case study with a 5-layered accurate SNN and approximate SNN is counter approximate part, and with approximation level of 0.1, and we are classifying MNIST dataset. So before attack, we have accuracy of accurate SNN like 97%, approximate SNN has 52%. But after the PGD attack with epsilon or perturbation budget 0.5, the accuracy of accurate SNN is not affected at all, or way less affected, like it goes to 95%. But in approximate SNN, there is a drastic drop in the classification accuracy. It goes to 40%. And here we have a 55% difference in the accuracy. But with another perturbation budget, like we can see that with epsilon 1.0, the accuracy of approximate SNN has like 68% difference in accuracy. So approximate SNNs are significantly less robust than accurate SNNs when we have an adversarial attack. Motivated by these observations, we have two novel contributions in our work. Let's investigate the robustness of AccSNNs extensively, and we wanted to identify the robustness-aware knobs so that we identify which approximation levels, the structural parameters, VTH, time steps, and quantization levels are good for robustness in AccSNNs. And then we also designed a security-aware design approach for frame-based and neuromorphic images, where we have precision scaling for frame-based images, and we have approximate quantized-aware filter for neuromorphic images, and these are the new approaches. In our security-aware design approach that we proposed, we first trained the SNN for some pre-trained weights that we get, and then we quantize those weights with int 8, FP32, FP16 quantizations. Then we apply approximation. For that, we first determine the approximation level. So basically, our approximation level is determined using the spiking probability, where that is like minimum of 1, Vm over Vth. So highest is 1 and minimum is Vm over Vth. Then we have some mean of the weights connected to the connection that we are deciding whether to skip or we should have. And then we have some the number of spikes and the time steps over here. After applying the approximation with this approximation level, we decide if there was a frame-based image or neuromorphic image. In case of neuromorphic image, we proceed with the AQF algorithm. But in the other case, like we just search for the best possible combination. And even after applying the AQF filtering, like we basically decide okay, which combination was good for VTH and time steps. So our algorithm outputs the best parameter configurations, but for the given set of inputs, like we determine the approximation level that is most suitable for our case. Now we represent actually the neuromorphic images in this form, like x, y, pt, where x and y are the x and y coordinates of the image, and p is the polarity changes in the brightness, t is the time step. In approximate quantized-aware filter, basically we remove the uncorrelated events from the neuromorphic images. The events with the low correlation, we consider them adversarial noisy. That's why. So first we quantize the dataset with a fixed quantization step. Then we find the uncorrelated events in each event E of the dataset, and we use a counter that is updated and flagged with each low correlation, and we remove the flagged uncorrelated events that we call E. So for investigating the robustness of our AccSNNs, we have a threat model. In that threat model, we are assuming that the adversary has partial knowledge about AccSNN. It knows the internal architecture of a classifier, but the motor parameters like VTS time steps, precedence scale, approximation levels are not known. And in attack generation process, the adversary tampers the input images in the prediction or the inference phase only, but it does not have access to the training data. And it finds the perturbation that maximizes the loss of a model on the input while keeping the perturbation budget lower than epsilon. In the experimental setup, we have two datasets like MNIST static dataset and or near frame-based dataset, and the other one is neuromorphic DVS128 Gesture. In the MNIST we have 7-layered SNN, and case of DVS we have 8-layered SNN. There is a difference in the architecture a bit, but the MNIST accuracy is like 97%, and DVS has like 92% without attack. That's a test accuracy. For static dataset, we are using BIM and PhD attacks. In DVS, like we are using sparse and frame attacks. We are using the perturbation budget of epsilon 1.0 because we observed that the accuracy of both the accurate SNN and AccSNN drops significantly after this value. So it becomes non-recoverable. That's why we are picking this for. And as an example, we are saying that it drops to 10% with epsilon 1.5. Here we can observe that with an increase in the approximation level and the perturbation budget, the accuracy decreases. And inaccurate SNN, when we compare before and after attack, the accuracy, so there is a 7% difference only. But in case of approximate SNN under BIM attack, the difference is 16%. Likewise, in case of BGD attack, the difference is 14% in case of accurate SNN, but 22% in case of approximate SNN. So from this, we can infer that AXSNN is 2x more vulnerable than accurate SNN in case of BIM attack, and 1.5x more vulnerable than accurate SNN in case of PGD attack. So here we can see that robustness varies with the change in approximation level. So under no attack, the accuracy of accurate SNN is 96% with MNIST classification. But when we change the approximation level, so without attack, the accuracy is even 93% for a 0.01 approximation level. But under attack, even drops to 77%. But if with another approximation level 0.1, it is 51% without attack, but after attack, it is 25%. So similar trend is observed in case of PIM attack. This was for PGD attack. In this case, we considered DVS gesture classification under sparse and frame attacks. So we have threshold voltage of 1.0 and time steps 80. So we observed that AccSNNs are vulnerable to neuromorphic attacks similar to accurate SNNs, because in both of the cases, accurate and approximate SNNs, the accuracy drops from 92% to 12% in sparse attack, but 92% to 10% in frame attack. Here we can see that under the PGD attack with MNIST classification for the precedence scale AccSNN, the accuracy without attack is like 96% before precedence scaling, but after precedence scaling of FP32, like accuracy we have 12%, and but it is very low in case of FP16 and int8. Now, if we change our VTH and time step for FP16, then the accuracy improves from 89% to 95%, and 95% is very close to 96% without attack. Likewise, when we talk about the BIM attack on precedence scale AccSNN with MNIST classification without attack or in the precedence scaling, the accuracy is around 97%. But after adversarial attack with like FE32, it is 82% accuracy, and we say like 15% accuracy loss. But it is very low in case of other two precedence scale SNNs, and when we change the threshold voltage and time steps, so now the accuracy for FP32 that was in the previous case like around 15%, now it is like only 1% having a difference with the accuracy without attack. From this, we can observe that the accuracy varies, or the robustness enhances or improves when we change the VTH time step, approximation level, and other parameters. Here, like we are, like we can observe, like for the VTH greater than 1.795 and approximation level greater than 0.1, we have certain deviations, and from the robustness trend, because the reason is SNNs lack performance efficiency at high VTH and approximation level. The spikes that trigger the LIF neurons at that point, like they may not cross the VTH. So here we are basically testing our algorithm, the security design approach algorithm for BIM, PGD, sparse, and frame attacks. We observed that we got different best suitable robustness settings for different VTH time steps and approximation level, quantization threshold, etc., or quantization type. So we can see that even we achieve like 96% accuracy with a change in the different parameters in case of MNIST dataset under attack. And similarly for the DVS Gesture 128, we have like even 90% and 91% accuracy under attack. We observed that under BIM attack, if the accuracy loss was 72%, but after precision scaling, we observed a 4x improvement in the accuracy, and accuracy loss that's like now it is 17% only. And likewise in DVS Gesture dataset, when we changed when we applied AQF filtering, so first it was 77% accuracy loss under the attack, Sparse Attack, but now it is like 2% accuracy loss only. That's like even a huge increase, like 38x improvement. So from this, like we infer that AccSNNs are more vulnerable to adversarial attacks as compared to accurate SNNs, but there could be a defense with precision scaling where we even achieve 4x robustness improvement in AccSNNs, and we can have defense through AQF filtering where we achieved like 38x improvement in the robustness. In future, this work can be extended to larger SNNs, and we would like to try with like a spiking ResNet that has the like 100 or so many layers. We also want to try some guided precision scaling and quantization filtering, like we can use some explainable AI or something like that in the future. Thank you so much for your time. Feel free to ask questions. You can also drop an email to me at any time. My email address is aisha.siddiq@mail.me0.edu.